3.2. So this is integration by parts. So in the previous section, I went over where the formula comes from and applied it to a few relatively simple examples. I'm going to apply it to a couple of harder ones here. So the formula is if you have some integral that you can break down into a function u and another function dv, then that's always going to be equal to u times v minus the integral of v du. That's the integration by parts formula. And it is a consequence of the product rule for derivatives. So because we have u's and v's in here, it also means we have substitutions to make the product rule work. So then for each problem, we have to decide what's the appropriate substitution. So for example, integral of 5x times e to the 3x dx. So we have to come up with u is something that's going to have to be differentiated because we have to come up with du. dv is something that has to be integrated to come up with a v. So when you look at this, you want to say, okay, what would differentiate nice and what would integrate nice? And sometimes it's like, it's kind of a toss-up as to which is which. Like e to the 3x, its derivative, is that nice? Yeah, it's nice. E to the 3x integral, just as nice. Okay, so that one can go either way. How about 5x, or just x? Which is easier for that one, the derivative or the integral? Derivative, right, because that drops the power down. Okay, so that would be my choice for the u. But you got to stop and you got to think about what should be my u and what should be my v. All right, so I would say then u is going to be 5x. And I would let dv equal what then?
E to the 3x.
E to the 3x dx.
dx.
Yeah, the dx has to go with it. So e to the 3x dx. So that gives me the left side of the formula. To get the right side of the formula, I have to go from a u to a du, which means I have to differentiate. So I'm going to take the derivative. Derivative of u is just du in the differential notation. The derivative of 5x is 5 dx. Yeah, we need that dx. From dv, I'm basically going to integrate both sides. And the integral of, that's really a 1 there with respect to v. What's its antiderivative?
3e to 3x.
The left side first.
Oh.
Integral of 1 dv is just v.
Yeah.
And on the other side, integral is going to be 1/3 e to 3x dx. And always, when you do an integral like that, you can double check what happens if you take the derivative. The answer would be e to the 3x and then multiply by 3, which cancels the 1/3. So once you do those two parts, you're ready to plug in to get your answer. So from here, let's see, I need u times v. My u is 5x. V is 1/3 e to the 3x. Minus v, 1/3 e to the 3x dx. We'll leave a little space there. Oh, wait a minute, something's wrong there. Oh, once I integrate, I get rid of the dx. That does not belong there. Sorry about that. So v is just 1/3 e to the 3x, and then du is 5 dx. So then you have this other integral to deal with. What's up?
Never mind.
I'm just going to shift this a little so I can finish the last line here. All right. So again, continuing, I can blend the constants in the first part, call that 5/3 times x times e to the 3x. Minus, pull out the constants, another 5/3. And then what's the antiderivative of e to the 3x?
30 to 3x.
130 to the 3x. And then we throw in our plus c because this is an indefinite interval.
Are you just taking the 1/3 out then?
Are you referring to this 1/3 here?
Mm-hmm.
Yeah, I took 5 times 1/3 and pulled that out right there.
Oh.
Could this be cleaned up a little bit? I guess I could factor the 5/3 and the e to the 3x out of each of those, but it doesn't really make things much better. So that's good enough. Sometimes you have to apply integration by parts more than once. So try the integral of x squared times the cosine of x dx. So we have to look at that and say, all right, what should our u be? What should the dv be? So the u is something that's easy to integrate, and u should be easy, something to differentiate, and the derivative should be better, easier than what you started with. And the integral that you choose should be something that integrates well and is usually better than what you started with, or no worse. So if any suggestions on u and dv here?
U should be x squared.
U should be x squared.
dv is cosine.
Color. And the nice thing about choosing u to be x squared is then du is 2x dx, which is an easier function to deal with than x squared. Yeah, so that's a good choice for that one. And that means then dv should be the cosine of x dx. Integrating that, we're going to get v equals antiderivative of the cosine, sine. And just double check, what's the derivative of the sine? Just the cosine, yeah. So whenever I integrate, especially sines and cosines, because this is the SIGM, I got to get right. I double check myself. All right, so we have all the pieces. Formula says take u times v first. So that's going to be x squared times the sine of x minus the integral. So again, this right here is u dv, right? So on the other side, I need v du. V is the sine of x. Du is 2x dx. And I just like to write them in that order, so I split it up just a little bit. Guess what?
Do it again.
Yeah, we have to do integration by parts again in order to do that right there.
Do you not pull the 2 out?
Yeah, you can pull the 2 out.
Okay.
Or you can leave it in there, it's up to you. So I could go off to another screen, pull that 2 out. So I'm going to have x squared times sine of x minus 2, and then I have to come up with an integration by parts solution for x times the sine of x dx. So new screen for that. So now I want the integral x times the sine of x. Guess what u is going to be? So that means du equals dx, and then dv sine of x dx. So remember, u gets differentiated, dv gets integrated because I need v back. And I'm thinking about cosine, but the derivative of the cosine is negative sine, so I need to adjust with a negative there. So then, rewriting this black integral, I get u times v, which is negative x times the cosine of x, minus the integral of v du, which is negative cosine of x dx. Enough the sines, SIGMs. And so that's going to be plus the integral of the cosine of x. What's the antiderivative of the cosine of x?
Sine.
Sine of x. Derivative of the sine is cosine of x, which takes me back to where I was there. Notice again, I took these two negatives and made it a plus. Now I have to stick that back into my other formula. I'll go back to my other page to do that. Negative x cosine of x plus sine of x. Back here, shrink a little. So I got to replace that right there. So now I get x squared times sine of x, which is sitting out front, minus 2 times, I'm going to put parentheses to be careful, because it's a negative x cosine of x. Oh, did I get that right? No, what was it? Yeah, plus sine of x. And then throw your plus c on the outside. Last step here would be to distribute that minus 2 into each part. So the final answer, just a little bit more room. Is going to be x squared times the sine of x plus 2x times the cosine of x minus 2 times the sine of x plus c. How do I check it? Take the derivative of this last line. You have the product rule applied multiple times. How many times did you have to do the product rule here?
3.
Twice.
Twice.
You have to do it here and there. How many times did we have to apply integration by parts?
3.
Twice. Yeah, they're directly related. Yeah. So all the integration by parts is the reverse of the power rule. Product rule, sorry. Yeah. Then you'd use the product rule here. That's going to end up with 2 things. You use it here. You can get another 2 things. Just a regular derivative on that, and then a whole bunch of stuff's going to cancel. What will be left in the end? Hopefully, just that if we're right. All right, one more of these, and then we're going to talk about some other trig integrals. Let's find an antiderivative for e to the x times the cosine of x. Dx. So a note on that last problem, by the way. The first problem I did, I had just an x times something like e to the x with a sine of x. That required 1 integration by parts.
X squared.
Then x squared required 2 integration by parts. Guess what x cubed require? 3. X to the 4th? 4. And it turns out there's actually a pattern to them that's kind of cute. But I don't think it's worth memorizing the formula. All right, this one. Suggestions. U dv.
I feel like it's easy both ways.
What's that?
I feel like it doesn't matter both ways.
Yeah, it turns out it doesn't matter in this case. So I'm going to go with kind of an order we did before. I'm going to let u equal e to the x. And I'm going to let dv equal cosine of x dx.
Wait, so you're saying there's a pattern to it, you know?
To the cubes and the squares and so on.
So then what happens if it's x? If x is in, you don't know what the number is for x. You know what I mean?
So the pattern I'm referring to is the way you end up, notice this has an x squared, a 2x, and an x, and it alternates between sine, cosine, and sine. And it also alternates from, let's see. Oh, the SIGNs kind of, they jump around a little bit for a couple of reasons. You've got a negative sign coming from integration by parts, and you have a negative sign coming from the trig functions. So that part's a little tricky.
I meant it more like it's x squared, so you do it twice.
Yeah, and x cubed you do 3 times.
Okay, then if it's e to the
X.
x.
Oh, what if it's e to the x? Yeah, how many
That's
times
what
do you
I'm
have to do that? Yeah. Okay. It turns out it's like infinitely many times, but there's a
That's what I
trick.
was gonna-
Okay, so I'll show you the trick. All right, so let's see. We apply integration by parts here. du is just e to the x dx. And v is sine of x, because the derivative of sine is just the cosine. So I don't have to mess with a negative sign there. All right, rewrite. It's always u times v first, so e to the x sine of x minus the integral of v du. Okay? And remember, when we made our substitution, we said this guy right here is u, and this stuff right there is dv. So on the other side, we switch it, and it's going to be v du. So v is sine of x, du is e to the x, so I'm going to write that as e to the x sine of x dx. Huh, interesting. Guess what we need to do?
Again.
Yeah, so now we need to look at this thing right here, and we need to apply integration by parts to that. I'm
We
gonna,
just keep,
what's that?
so we're just gonna get stuck in a loop.
Sort of, but I'm gonna show you a trick to end the loop.
Okay.
Yeah, so there is a loop, but we're gonna figure out how to end it. All right, so new page. So just summarize where we are. We started off with the integral of e to the x cosine, and e to the x cosine of x, that's better. And we found that that's equal to e to the x sine of x minus the integral of e to the x sine of x dx. And so now we need to do integration by parts again. So let's stick with the same pattern. Let's let u equal e to the x and dv equals sine of x dx. du is e to the x dx, and v integrating is what? Negative cosine of x. So I'm going to rewrite the whole thing starting from there. So from before, I have my e to the x sine of x minus, now I get to apply this new integration by parts. So I'm going to use a parentheses because I'm going to have to distribute that minus. I'm going to be super careful with signs here, SIGNs. All right, my new uv is a e to the x times negative cosine of x, so I'm going to call that negative e to the x cosine of x. Integration by parts formula says minus comes next. Integral of v du. So I've got another negative inside there, e to the x cosine of x dx. Okay, cleaning up. E to the x sine of x minus a negative, so that's a plus e to the x cosine of x. Okay, so this is where it gets a little interesting. I have minus of a negative. Okay.
What's U?
So that's going to be a minus the integral of e to the x cosine of x dx. Yes, and that's a good thing. Here's why. This is what I started with, is it not? This is an equal sign right here, right? What's on the other side of the equal sign?
They cancel.
They don't cancel. Because if I want to get this minus to the other side, what am I going to have to do with it? I'm going to have to add, oops, switch colors. I'm going to have to add e to the x cosine of x dx. So that means I have to do the same to this side. I have to add to that the integral of e to the x cosine of x dx. Oops, forgot my dx up there, sorry. Illegal. What happens if I add something to itself?
One. No.
It doubles. You get two of those. Okay, so here's where I'm at now. New page. I now have, oops, what happened there? Oh. There we go. I now have twice the integral of e to the x cosine of x is equal to e to the x sine of x plus e to the x cosine of x. We removed that guy to the left. That's where the 2 came from right here. So now I have e to the x sine of x plus e to the x cosine of x. Just divide by 2. Yeah. So now I know that the integral of e to the x cosine of x is equal to 1/2 of e to the x sine of x plus 1/2 of e to the x cosine of x. And I shouldn't forget about my plus c.
What about, is there dx in that integral?
Oh, sorry, I'm being illegal again. Now, jump and Carter, so.
Can you go back a couple slides?
Yeah.
Yeah, that one. So the second line from the bottom, that that one.
Yeah.
How did the negative integral negative? How did that still become a negative?
Because I have a minus here, here, and there. So that's basically -1 times -1 times -1 gives me a negative.
We can call it positive. And it's still,
So those would make a positive, and then when you.
You're talking about right here or right here?
Wait.
Right here?
Yeah.
Okay, so
So you make that
these
a
two
positive.
negatives become a plus, right?
Oh, because those are inside the parentheses.
Yeah, because
So
that's
it
inside the
goes
parentheses
to all of
here.
them. Okay.
Yeah, so I'm distributing that negative.
Okay.
So I have 1, 2, 3 negatives.
Yeah. Okay. Now I get that.
Yeah, so, and with integration by parts, with any anytime you have to apply it more than once, you have SIGN issues to worry about. That's always going to happen. And you got to think about distributing that minus sign there.
Okay, can you go back to the other page?
and that's your answer?
That's the answer right there. I could clean it up a little bit by factoring out the 1/2 e to the x. So that would be an alternative way to write it. That alternative way?
No,
The whole
the
thing?
1/2.
The 1/2 part? Yeah, that happens a lot. And that's about the hardest integration. The part's where you do it a couple of times and you realize, oh shit, I just made a cycle. Now, notice something about the way I did this. I was consistent in my choice of u. When we first started this, I believe it was Carter that said, well, I don't think it matters whether we choose u to be e to the x or u to be cosine of x. And that is true. But if you start off with u is equal to e to the x, then stick with it. Because if you switch it in the next round, then everything cancels out on you and you get nowhere. Instead of a loop, you get a dead end.
So if we were to pick cosine to be the u,
Then the second time we would pick sine to be the u.
okay.
Yeah,
So but we'd get the same thing.
But you'd still get the same thing. What you'd find is, oh, it's the opposite on the other side, added over and it doubles, and you just solved it. Yeah. But you got to be consistent. If you're not consistent in this choice, both times, then just things disappear on you and you end up with where you started and no solution. Okay, so integration by parts is pretty powerful. In the video I did yesterday, I showed that we could use it to find the natural logs antiderivative. We could use it to find the arc. I think I did arc sine in that video yesterday. So there's a ton of applications for it that allow us to do things we couldn't do before. The next thing we're going to screw around with in section 3.2 is trig functions. And the big thing about trig functions, there's two tricks. One trick, trig identities. So you know that that note sheet we developed for the second test? We're going to continue developing that for the final exam, and we're going to probably want some trig identities because you guys haven't done trig in a while. My guess is some of those identities have fled your memory. Okay.
We are going to get one for the final too.
Yes.
It's going to be the same one, we're just adding one to it.
Yeah, we're just going to add on to it. So trig identity is going to be important. Second thing that's going to be important is just regular U-substitutions. So what trig identities are we going to want to use? Well, popular trig identities, Pythagorean theorem, sine squared of x plus cosine squared of x equals 1, which allows us to replace a sine squared or a cosine squared. Right? Alternatives of this are sine squared of x equals 1 minus cosine squared. Or we could say the cosine squared of x is equal to 1 minus the sine squared of x. Other identities that we're going to need, trig identities. Math is fun. What do their trig identities look like? There's the Pythagorean, all the versions of the Pythagorean. Yeah, so other versions are like, it might be helpful to know that the secant squared is 1 plus the tangent squared. Oh, I'm not familiar with the magic hexagon. I'll have to come back and look at that. Other functions that we're going to find useful are the cosine double angle formula. So where's my notes? Flashbacks. Flashbacks to trigonometry. So
I think it was a simpler time.
cosine squared of x minus the sine squared of x. So if that was a plus, that would be equal to 1. If the cosine is first and it's a minus, then that's the cosine of 2x. Now, variations on the cosine double angle formula. Cosine squared can be rewritten as 1 minus the sine squared, right? Right, that was just on the previous page. And so I could replace cosine squared with 1 minus sine squared, which means an alternative here is 1 minus twice the sine squared. Alternatively, use a different color, I could have replaced the sine squared with 1 minus cosine squared, in which case I would get twice the cosine squared. Oh, sorry, minus 1. Okay, so this is helpful because it gives me another way to rewrite cosine squared. So if I solve this black equation for cosine squared, Well, I would have to add 1 to the other side, right? So then I would get cosine of 2x plus 1. And then I would have to divide by 2. And this formula right here, anybody know what this one's called, that second version of this? That's called the half angle formula. Because if I let 2x equal theta, then x would be theta over 2. And so then I can rewrite this formula. Red, x is theta over 2, so this gives me the cosine squared of theta over 2 is equal to the cosine of theta, because I said theta is 2x plus 1 over 2. And if you wanted the cosine on this side all by itself, you would just take the square root. That's what's called the half angle formula in trigonometry, because it deals with half angles. Guess what we can do with this one up here? That's where the half angle for the sine comes from. So I want to solve this for sine squared. Okay, so let me bring that to a new page. Cosine of 2x is equal to 1 minus twice sine squared of x. So I want to get the sine squared alone, so I would subtract 1 to the other side. That gives me negative 2 sine of x, sine squared, sorry. Divide by negative 2. Now, dividing by negative 2 here, I don't like the negative in the bottom, so I'm going to distribute the negative through the top, in which case I'm going to rewrite it as 1 minus the cosine 2x. Then I get to put a positive 2 in the bottom. So I just multiply top and bottom by negative 1 to make that happen. And what's on the other side now? Sine squared by just the sine squared. And then if we take the square root and do a variable substitution, this is what's called the half angle formula. Okay, I like the squared versions of these with the x where it is, so we're going to call these the half angle formulas for what we're doing. So here's one of them. The other one would be the cosine squared of x is equal to 1 plus the cosine of 2x over 2. So those two are going to be helpful formulas. So let's do a couple of integrals where we're going to use U-substitutions and trig identities to help us through them. So first, I'll just give you the ideal cases, and then we just have to muck around with the other cases, so this is going to take us into tomorrow. The ideal case is if I have something like the integral of the sine to some power n of x times the cosine of x. So n could be the second power, or the third power, or the 10th power. I really don't care what it is. The nice thing about things that look like this is it's set up for me to do a U substitution. Guess what I would let U be in this case? N. Not n, the sine. Yeah, because the sine is an inner function to the power n. So I would, let's say, let's let U equal the sine of x. So what would du be for this situation?
Negative.
Just be the cosine of x dx. Well, isn't that what's sitting right there? Yeah, there's my du. So then rewriting this integral, I get the integral of u to the n du. Well, hell, that's easy. What's the antiderivative of u to some power? Well, we increase that power by 1 and then divide by n plus 1. What's u really here in this case? Sine, so that means this integral must be equal to the sine to the power n plus 1 now of x, divided by whatever n plus 1 is. So if we started off with the sine to the 5th power, this would be a sine to the 6th power, plus c. We're done. Problems happen is if that cosine is to some other power besides 1. Then a U substitution doesn't work as efficiently. That was the problem here. All right, so let's try something medium hard. Suppose I just have the sine squared of x, but the cosine was missing. And do a U substitution now because there's no du. But we just went over some very clever trig identities, like the half angle formula. What's the half angle formula say for sine squared? Yeah, it says this right here is just 1 minus the cosine of 2x all over 2. So these integrals are exactly the same, because that's an identity. I would rewrite that by pulling that 2 out as a 1/2. So now I need to integrate 1 minus the cosine of 2x dx. So let's see. All right, so finding an antiderivative, the 1/2 is just chilling out as a multiple in front. What's the antiderivative for 1?
X.
X. Now ignore the 2x for just a sec. What's an antiderivative for the cosine?
Or sine.
It's just sine, because the derivative of sine is cosine, right? So this minus hangs out. This is going to be the sine of 2x. But the problem there is if I take the derivative of the sine of 2x, what do I get? I should get twice the cosine. So my guess is I need a 1/2 multiple there. Because when I apply the chain rule to the 2x, 2 times 1/2 cancels. So that should be the 1/2 sine of 2x is the antiderivative for the cosine of 2x. If that's messing with your mind, then just do a u equals 2x and follow your U substitution. Plus c, and we're done. All right, we have time for one more, I think. Ooh, that didn't print well. What? Sorry, I printed out your homework and it looks very bizarre. Let me check it here. Did that happen here too? Integration by parts. Printer just messed up. Oh, that looks okay there. Okay. Okay. Well, let's try this one, shall we? Tangent to the 5th power of x over 6 times secant to the 2nd power of x over 6. What can we do with this? So I'm going to screenshot that. This is, I don't know. Hang on, I'll figure it out. I think it's number 2 or 3.
Oh, no.
All right, so that was question number 2, yeah. It's a beauty. All right, so we have tangent and secant, and so I got to think about their relationship to one another. Like, what's the derivative of tangent?
Secant squared.
Oh my, there's a secant squared sitting right there. Score! Okay, so it's not as bad as it looks.
So the u would be tangent.
Yeah, watch what happens though. Yeah, if we let u be the tangent, right? Because u is the inner function of x over 6. Then du would be the secant squared of x over 6 times 1/6 according to the chain rule. Oh, and I'm missing my dx. Let's fix that. Oh well, dx. All right, let's see, what's the problem? I'm missing a multiple of 1/6.
So you use times 6.
So I could multiply 6 to the other side. So I could say this is 6 times du equals the secant squared of x over 6 dx. All right, so for my substitution then, switch colors, I get the integral of u to the 5th, right? Because u is my tangent. And then the secant squared dx is 6 du. So we can pull out the 6.
Actually, you can leave it.
Actually, we could leave it in. Yeah, this is kind of nice. Because think about it. What's the antiderivative of u to the 5th? It's u to the 6 times 1/6, but we got a 6 hanging out there conveniently. So this is just u to the 6th. Let's see. Double check. What's the derivative of u to the 6th? Isn't it 6 u to the 5th? Right? So now am I ready to state my final answer? What's u really?
Tangent.
And now it's to the 6th of x over 6. Let's see.
Wasn't so
Oh, so bad. Yeah, of course it was. Some of these look as bad as they are. Oof. Okay. So it's going to get more interesting. So what we need to do next is we need to figure out is what if there's multiple powers of each that don't match the way they hope they do. Like suppose I had the integral of sine to the 7th power of x times the cosine to the 3rd power of x dx. That's not that ideal case I stated first, right? If this was just a cosine there, not a cosine cubed, I'm set. So I'm going to have to apply some identities to this before I can use a substitution. So we'll do that next class.
So does that mean that the assignment's pushed back?
Isn't it due tomorrow?
It's due today.
This one's due today?
No.
No, integration by parts is due today because I started that yesterday.
Oh, okay.
Yes.
Okay.
But if somebody says please, I could move it.
Children's posted at 4 a.m. this assignment number 6.
Yes, I saw that.